So, welcome to this module, and in last module what we have seen? We have seen the RC phase shift oscillator. In this module let us see another oscillator which is the Wein bridge oscillator, Now, in Wein bridge oscillator we do not require the feedback or the feedback of 180 degree, because the phase shift phase at the output of the Wein bridge is 0. So, we do not really require an external RNC to get back another 180 degree and feed it to the input. So, now when we talk about Wein bridge oscillator, how Wein bridge oscillator operates we have seen in the theory class, but we will again quickly see in just 1 or 2 slide how the Wein bridge oscillator operates, so that you can understand when we do the experiments. At the same time we will see some problems that if for a given problem how it is solution, and then how you can design this Wein bridge oscillators, alright. So, when you talk about Wein bridge oscillator, one thing that you have to understand is that the in this kind of oscillator. So, let us go to the screen so that it is easy, and we do not really waste our time. The Wein bridge oscillator can be designed by using op amp, where resistance R and capacitor C determine the frequency of oscillation. This is shown in figure. So, if you see this one, right, what you see here? Here you see that there is a capacitor R, capacitor C and resistor R. So, these two arms are the arms that determines the frequency, they are frequency determining arms, alright. So, resistor R and capacitor C determines the frequency of oscillation. So, in this circuit feedback is given to the non inverting terminal. As you can see, the feedback is given from this circuit. If you see, this feedback is given to the non inverting terminal to ensure 0 degree phase shift. Here we do not require 180 degree phase shift, right. That is why we are giving the feedback to the non inverting input, okay. And for the oscillations to occur here, we have seen in theory that the gain of op amp must be equal to or greater than 3, gain should be equal to or greater than 3, we have seen it, right. And this can be adjusted by RF and RI, this can be adjusted by feedback resistor RF and input resistor RI. So, where is feedback resistor RF? This is your RF, this is your RI, because this is the input to the op amp, right. So, here we have feedback resistor RF, we have feedback resistor RI, and the ratio of the resistance part, feedback part to input should be greater than equal to 2. Why greater than equal to 2? Because if I have a gain, which is equals to 3, or gain is greater than equal to 3, right, my Bar-Coushain criteria says A into beta should be 1, and phase shift should be 0, phase shift should be 0. So, if my A is greater than equal to 3, my beta should be greater than or equal to 1 by 3, right. But if I have this one, then only I can have this particular gain greater than 3, right. Why? Because it is a non inverting amplifier. So, formula is 1 plus RF by RI. If it is greater than equal to 2, if it is equal to 2, this will be 3. So, my gain is equal to 3, this is satisfied, alright. So, that is why we say that the ratio of the feedback resistor, should be greater than or equal to 2. Okay, understood. Now, frequency of oscillator for this particular circuit, frequency formula is f equals to 1 upon 2 pi RC. So, easy, right, easy to remember. Frequency is nothing but 1 upon 2 pi RC. Okay. This is the case when we are talking about Wein bridge oscillator. the case when we are talking about Wein bridge oscillator. So, let us see an example, of a Wein bridge oscillator and determine the maximum and minimum frequency. So, what is our question? Our question or our problem is that we have to determine the maximum and the minimum frequency of oscillations of a Wein bridge oscillator circuit, right. What do we determine? Maximum and minimum frequency, f minimum, f maximum. Having a resistor of 10 kilo ohm, R is given 10 kilo ohm, variable capacitor of 1 nanofarad to 1000 nanofarad, C equals to 1 nanofarad to 1000 nanofarad. If this is the condition that is given, right, let us calculate the f minimum and f maximum. Now, we know that in case of Wein bridge oscillator, the formula is f equals to 1 by 2 pi R C, we know this, right. So, if I want to measure the minimum, f minimum, then what will I do? I will have f minimum 1 upon 2 pi, R we know 10 kilo ohm, C for minimum frequency, C should be maximum. So, I consider the maximum value 1000 nanofarad, right, because it is inversely proportional, that is why C should be maximum to find the minimum f minimum. So, my value is 15.9 hertz, hertz. But for the higher frequency, Wein bridge oscillator for highest frequency, that is your f max, my formula would be same, f equals to 1 upon 2 pi R C, but here my capacitor value would be 1 nanofarad. And if I use this particular values, what I am having? I am having a frequency f max equals to 15.915 kilohertz. So, if you are given an example like this or a problem like this, you should be able to solve within 1 minute or within 2 minutes, okay, within 2 minutes. Why? Because I am taking long time, so that you understand clearly, but when you want to solve, so easy. If you are given this maximum minimum frequency oscillation Wein bridge oscillator, okay, R is given 10 kilo ohm, C is given from 1 nanofarad to 1000 nanofarad, alright. My formula for frequency is nothing but f equals to 1 by 2 pi R C. So, what is said 1 upon 2 pi into 10 kilo ohm into C, which is 1000 nanofarad, this will be my f minimum. This when I calculate by calculator, I will have the value equal to nothing but 15.9 hertz, right. Same way for f maximum, I will say f maximum equals to 1 by 2 pi into 10 kilo ohm into 10 nanofarad, right, 10 or 1 nanofarad, which is maximum minimum. So, 1 nanofarad, right. If I use this formula, my f maximum would be nothing but 15.915 kilohertz, done, right. So, I can find this formula because it is already written here, that is why I can do it within 1 minute. But if you want to use calculator, that is why I said around 2 minutes will require or less than that to require to find the solution for such a problem, right. So, when you are given a problem, don't get nervous, right. It is very easy. F x minimum, f x maximum or f minimum, f maximum, we can find it for the given set of values, that is our R, that is our C, alright. So, let us go to the next slide, and next slide is our second problem, example 2. So, we are making example little bit tougher, let us see what is the question. The question given is that for a Wein bridge oscillator is required to generate a sinusoidal waveform or 5200 hertz, or we can say this one is nothing but 5.2 kilohertz, right. Calculate the values of frequency determining resistors R1 and R2. R1 is not known, R2 is not known, and the capacitor C1 and C2 to produce required frequency. C1 not known, C2 not known. Also, if the oscillator circuit is based around a non inverting operation amplifier, very important thing is given. determine the minimum values of gain resistors, we have to find RF, we have to find Rin to produce required oscillations. Finally, draw the resulting oscillator circuit. Oh my god, so big problem, right. Is it difficult? Is it difficult? What you are telling, I cannot hear, and that is the beauty of the course, that I cannot hear what you say, but I can understand what you say when you let me know through the forum, right. If you have any difficulty, if you do not understand, if you find the solution and you are not matching, the solution is not matching, ask, but first try, alright. So, problem is easy, I am just kidding, problem is really easy, right. Let us see how we can solve for the given set of values, how we can solve this problem, alright. Starting with, we know frequency formula, right, f equals to 1 upon 2 pi RC, 5.2 kilohertz is given, this much is given. Okay. Now, the frequency of oscillators for Wein bridge oscillator was given this one. If resistor R1 equals to R2 and C1 equals to C2, we assume a value of feedback capacitors to be 3 nanofarad. Let us assume it to be 3 nanofarad. Then the corresponding value of feedback resistor is calculated as, so if I have the value which is about 3 nanofarad, right, my R value would be, if I have f equals to 1 by 2 pi RC, R equals to 1 by 2 pi FC, I have considered C equals to 3 nanofarad, then my R value would be 10.2 kilo ohm. This is easy, one assumption we have made, C equals to 3 nanofarad. Now for sinusoidal oscillations to begin, right, the voltage gain must be equal to or greater than 3. We know that, right, in Wein bridge oscillator the voltage gain should be greater than or equal to 3. For non-inverting amplifier, the value set by the feedback resistor network is given as 1 by R3 by R4. We already know this, right. We have just designed this, which is similar to your this one, this circuit with this. It is similar circuit, right. It is similar circuit. Just we have just placed the component so that it looks it is looking different, otherwise it is same circuit. Now we know that is the input, we have to consider the non-inverting amplifier, right. We have to consider non-inverting amplifier. Now we know that the gain should be, the gain for Wein bridge oscillator should be greater than or equal to 3. Then we should have a feedback resistor which is R3 by R4, 1 plus R3 by R4. Why? Because it is non-inverting amplifier. This should be equal to 3 minimum. This should be equal to 3. So now we have 1 plus R3 by R4 equals to 3, or R3 by R4 equals to 2, right, because 1 plus R3 by R4 equals to 3 implies R3 by R4 equals to 3 minus 1 equals to 2. So now I have to have a ratio of R3 by R4 equal to 2. So I can assume any value, R3 100 kilo ohm, R4 50 kilo ohm. My answer is R3 by R4 equals to 2, right. So using this we can find the value of R3 R4. Okay, feedback values found, R found, capacitor we have considered 3 nanofarad, right. So while a gain of 3 is minimum value are required to ensure oscillations, in reality a value little bit higher than it is required generally. If we assume a gain of 3.1, then resistance R4 calculated to be given as 47 kilo ohms, alright, which is this one. This gives us final Wein bridge oscillator circuit as shown here, right. So let us see what we have done for this particular problem, right. Quickly we have found f formula, this frequency formula, right. From that we know 1 upon 2 pi RC, we have assumed C equals to 3 nanofarad. For that we got a value of R to be 10.2 kilo ohm. Then we know that it is a non-inverting amplifier, it is a non-inverting op amp configuration. For non-inverting op amp we know that the gain in the case of Wein bridge oscillator should be A is greater than or equal to 3, right. So for that we have greater than or equal to 3. Now non-inverting complex amplifier we have formula 1 plus Rf by Rin, 1 plus Rf by Rin equals to 3. right. From that we have found RF and RF, RF and RIN is nothing but R3 and R4, R3 and R4. From that we found what is value of R3, what is value of R4. This is the ideal situation. So, that is why to have the oscillations to start, we need to have a gain or the value of R3 by R4 or value of gain actually should be little bit more than 3, which is about 3.1. In that case, if I have 3.1, my R4 value will be about 47 kilo ohm, and the circuit is shown here. So, this is how you can solve an example for a given Wein bridge oscillator. Nice, good. So what? So what? Now the real thing is, can we implement this circuit on the breadboard? Can we implement this circuit on the breadboard? Right? That is the idea. So, we have this again the table. You can calculate the frequency. You calculate the frequency by yourself. Right now, what what I want to show you is, if I connect the Wein bridge oscillator in this particular configuration, whether we are able to see the output voltage, output waveforms in the digital in the DSO, So, we have to connect the circuit as shown here. Observe the output at pin number 6 and with respect to ground, measure the frequency oscillation and match it with theoretical value. Theoretical value will match later. Right now, let us just see quickly that if I connect a DSO at output here or here with respect to ground, what kind of signals I obtain at the output. Again, you can see here we are not giving any input in particular to say, right. So, let us see how it looks like on the breadboard. Let us see on the breadboard how it looks like. So, if we see, we will call Anil to help us. So, Anil is expert in oscillators. So, that is why we are calling him. I am just kidding. All the teaching assistants that will help you in this particular course, they have a good amount of expertise in analog electronics, and I will be there to help you out. So, feel free if you have any questions. The only thing that I will request is first try and then ask. Okay. So, if you see this circuit, which is the Wein bridge oscillator, you can see, as you can see here, the R and C, these are the arms that are used for adjusting the frequency, and now we have connected the oscilloscope, which is here, right, which is connected to the output of the Wein bridge oscillator, and let us see what is the output in terms of in the oscilloscope. First we have to apply the bias voltage. So, now here right now the DC the supply was off, he just turned it on, and the applied voltage or bias voltage is plus minus 15, and you can see on the oscilloscope, that you can see immediately generation of the oscillations. Now, if you here also, if I change the fourth resistor, if you come back to the circuit, you will see that the fourth resistor is a variable resistor. We have used a potentiometer. You can show the potentiometer. So, you see here we are using the potentiometer as a fourth resistor in this Wein bridge oscillator. So, if I change the value of this resistance, what will happen? That means I am changing the gain. If I am changing this resistor, then what will happen? You see on the oscilloscope, if you can magnify, yes. So, now I am changing the value of resistor, and you can see immediately a change in the oscillation. You are able to see, right? You guys are able to see now. So, this is how the Wein bridge oscillator would work. If I keep on, if I have a variable resistor, I can keep on changing the oscillation. Alright. So, what I understand is, now you at least know, right, how a Wein bridge oscillator would work, and what will happen if I keep changing the values of resistors. Can I design a Wein bridge oscillator? Yes. We have taken two examples. By changing the by getting some of the values, we can determine F minimum. By understanding the values, we can determine F maximum, right. By changing the value of resistors, we can get the output of our desired frequency, and we can also use this Wein bridge oscillator with a phase shift of 0 degree, because there is no phase shift at the output of the Wein bridge, and that is why we are using operational amplifier and we are applying the output from the bridge to the operational amplifier non inverting terminal, because we do not need another phase shift, because here the phase is 0 degree. So, total we have to understand is one thing is your gain and your feedback network should be equal to 1. The mode of your gain and feedback network should be 1 and the phase shift should be 0. We understood this, we kept the same criteria, we tried to see and implement it on the board, and we were able to see that the oscillations, generation of oscillations by changing the resistor. So, here the main thing here compared to the earlier oscillator is, here we have we do not have to give a separate phase shift of 180 degree, another phase shift of 180 degree, alright. So, I hope that you understood what is the how we can use the Wein bridge oscillator and how we can implement the Wein bridge oscillator using the operational amplifier and using capacitors and resistors. And here also one thing is very important, we are not applying any input signal, we are not applying external input signal, the input is generated by within the op amp by itself, alright. So, you just look at the video once again, read it, understand it, right. If you have difficulties, if you do not understand, you are free to ask me any question, alright. So, till then you take care, I will see you in the next module.